Exergy analysis of proposed Vesta 164 8 MW wind turbine in Portugal Cove, Newfoundland and Labrador, Canada. Presented by Olajide Michael Busayo and Osho Rashid Abiodun. Introduction. Globally, there has been heavy dependence on fossil fuel as the major source of energy for several decades. And the increasing global energy demand has continued to accelerate the depletion rate of the fossil fuels. And in addition to this resource depletion, the combustion of fossil fuel produces greenhouse and harmful gases in the atmosphere. Example of such greenhouse gases are carbon dioxide, sulfur oxide, and nitrous oxide. And to overcome this challenge, several countries have continuously invested in the exploration and use of clean, environmentally friendly, renewable sources. One of the world's renewable energy resources is wind. And the best way of using wind is to produce electrical energy. Considering the rising use of wind turbine and their environmental benefits such as zero harmful emission during operation, the potential of this system in diverse areas is essential. And several types of research has been carried out in this field of energy, exergy, and economic analysis of wind turbine in recent times. And the aim and objectives of the study. The aim and objective of this study is to study the exergy of Vesta 164 8 MW wind turbine at the proposed wind farm in Portugal Cove, Newfoundland. Also, we want to compute the energy and exergy efficiency of the wind turbine. And lastly, we want to investigate the variation of exergy efficiency with varying temperature, pressure, and wind speed in order to assess the performance of the wind turbine. The system specification. The specification of the wind turbine that was used in this work is as stated below. We have the rated power, which is 8 megawatts. The cutting speed is 4.0 meter per second. The cutout wind speed is 25.0 meter per second. The rotor diameter 164 meter. Numbers of blade is 3. The type of generator is permanent magnet. The tip speed is 104 meter per second. The voltage is 66,000 volt, and the grid frequency is 50 hertz. Assumption. The following assumptions were made in the course of this research work. We have the wind flow was assumed to be unidirectional and steady. Temperature and pressure differences of the wind turbine were taken into account, while the heat transfer or phase changes and the effect of humidity were ignored. Literature review. As we know that energy analysis is an important tool for assessing the performance of energy system, and it has been applied or used into wind turbine in order to evaluate their efficiency and effectiveness. The use of energy analysis has been applied to wind turbine to evaluate their performance as well as identify areas for improvement. According to Kumar et al. 2007, in his energy analysis, he studied how different wind turbine wind speed affect turbine efficiency, and the study revealed that the higher the wind speed, the higher the turbine efficiency due to increased airfoil lift.
Next, we will be looking at the methodology that we employed. Here, we looked at the energy analysis as well as the exergy analysis of the control volume, which is the wind turbine itself. And looking at the energy analysis, we employed the energy balance equation as represented in the equations below. The first is energy equals to energy out, and then we looked at the rate of change of the energy in the control volume is here in equation 2. And finally, we look at the thermal efficiency of the wind turbine, and it's represented as energy out in relation to the energy in. Next, we shall be looking at the exergy analysis, and here we are looking at the impact of the environmental conditions like pressure, temperature, and wind speed on the efficiency of the system. And here we are looking at this equation below. Exergy out equals to exergy in plus exergy destroyed. And then we should be looking at the next expression, which takes into cognizance the entropy of the system, which is represented as exergy in equals to exergy out plus the change in entropy, and then the change in entropy. Of course, the heat exchange with the environment. And finally, we're looking at the exergy efficiency relation, which is the relation between the exergy health result and discussion. Here we shall be discussing our results as below. The first graph shows the average temperature of the turbine in 12 months from January to December. And here we can see that the average temperature is minimum in February and maximum. The next graph shows the average monthly pressure from January to December. And here we can see from the graph that the average pressure was maximum in September, and of course it was minimum. Next is the graph that shows the wind variation prevalent in Portugal Cove, which is the site of the proposed installation of the wind turbine. And here we can see that the wind speed, the average wind speed was minimum in June and maximum in. And the next slide would show the impact of this variation in the environmental conditions as we have outlined: the wind speed, the temperature, and the pressure on the energy and the exergy efficiency of the control volume, which is the wind turbine. From the graph, we can see that the energy and the exergy efficiencies were maximum in February and minimum in July. And from the previous slide, we can see that the energy and the exergy efficiency that were maximum in February is also linked to the wind speed, which was also maximum in the same month. Wind speed was maximum in February, and so we have it that energy and exergy efficiency were also maximum in February. And so we can see that this corresponds to when there is maximum wind speed and minimum wind speed respectively. When we have maximum wind speed, we have maximum efficiency. When we have minimum wind speed, efficiency. And then we go to conclusion. From the work that we have done so far, we can conclude as follows. Number one, that the results reveal that both the energy and the exergy efficiency were maximum in the month of February. We can also see that the energy efficiency was 50% in February, which is the maximum, and the exergy was 41%, which is also the maximum in the same month. And this corresponds to when the wind speed was maximum and the temperature and the pressure were also minimum in the same month. We can also see that both the energy and the exergy efficiency were lowest in June, and this corresponds to when the wind speed was lowest, while both the pressure and temperature were quite high in the month of June. The difference between the temperature and pressure is most significant in February due to high wind velocity, resulting in the slightest energy destruction and the highest exergy efficiency. And we can also see that exergy efficiency varied between 18 and 41%, which was lower than energy efficiency, which lie within 24 and 50%. We can also conclude that the maximum energy efficiency in the month of February is substantiated by the minimum energy destruction during this month. Of course, whenever we have minimum destruction of exergy, we have maximum exergy efficiency. We can hereby conclude that though exergy analysis results are lower than those of energy analysis, but they show real assessment and performance of wind turbine that can assist engineers, government administrators, and the stakeholders in the energy sector to articulate policies that can raise the actual performance of wind energy plants. Thank you.